Hello my friends and welcome back to the You Can Do TV channel. Molten blast furnace slag is collected from the bottom of the furnace and transferred through a trough into a slag granulation tank. The slag tanks are transported away for cooling. Workers pour the slag in the tank into a trough and use high-pressure water jets to rapidly cool the slag, causing it to vitrified into a glass bead material. The resulting mixture of water and granulated slag flows into a settling tank, where the slag is separated from the water. After dewatering, the slag is transported by truck to the processing site. There, the slag is crushed and screened to obtain different aggregates of 0 to 8 millimeters, 8 to 16 millimeters, 16 to 32 millimeters, 32 to 63 millimeters, 0 to 63 millimeters, and 63 to 200 millimeters. Water is sprayed onto the slag dumps to reduce dust, cool the slag, and stabilize the dump. Unusable impurities after screening will be dumped and temporarily stored in a separate storage area, awaiting processing. The collected aggregate components will be collected in one place. Each component is carefully classified and stored for later use. At Alcoa Warwick, the smelting process begins in the green mill, where carbon anodes are formed from petroleum and metallurgical coke byproducts. These anodes are baked in a ring furnace at 2000 degrees Fahrenheit for 5 to 6 days. Alumina shipped from countries like Australia is conveyed to pot rooms and placed in pots containing molten cryolite and the baked anodes. Each pot is charged with 130,000 amps of electricity, separating aluminum from oxygen. The heavier aluminum sinks to the bottom and is extracted through a process called tapping. Impurities are skimmed off before the molten metal is sent to the ingot department for casting. The hot rolling process begins when the steel plates are heated evenly in a mobile beam furnace, which minimizes surface defects. The heated steel plates are then rolled through a 7-foot CVC plus finisher, which ensures precise flatness of the steel strip. Finally, the steel strip passes through a cascade cooler, where advanced cooling controls adapt the various steel grades for optimal mechanical properties. The final product is a hot-rolled coil. The TMT steel production process at AKS begins with heating prime quality billets in a reheating furnace. Once heated, high-pressure water jets remove surface oxidation through a descaling process while maintaining a consistent billet temperature. The billets then enter the rolling mill, which has 18 mill stands divided into roughing, intermediate, and finishing zones. AKS uses a combination of horizontal and vertical stands, which roll billets into desired shapes without turning, preserving internal structure and increasing material density. After rolling, the bars undergo thermomechanical treatment. They pass through a rapid cooling system that lowers the surface temperature while retaining a hot core, creating layered structures for enhanced strength and flexibility. The bars are then cooled on a 12-meter-long cooling bed. Subsequently, automated machines bind the finished steel bars. Each batch undergoes rigorous testing in AKS's quality laboratory, checking chemical composition, mechanical properties, and elongation, ensuring compliance with national and international standards. AKS uses an electric arc furnace, unlike common induction furnaces, to produce purified billets, enabling the manufacture of world-class TMT bars with 22% elongation, superior to the national average of 14%. threaded rods at Liberty Ostrava are produced from continuously cast square bars measuring between 130 and 180 millimeters and weighing between 1.3 and 3 tons. The bars are first heated to 1,150 degrees Celsius in a reheat furnace. Once they have reached the desired temperature, they pass through a rolling mill, where they are shaped into long bars with diameters between 15 and 75 millimeters. The rolled bars are then threaded using specialized threading equipment. Depending on the intended application, two different cooling processes are used. For bars intended for geotechnical purposes or as reinforcement in concrete, a controlled cooling process is used, reducing the temperature to around 500 degrees Celsius. The bars are cooled carefully to ensure the desired mechanical properties. For mining and construction purposes such as formwork or anchoring, the bars are left to cool naturally on a cooling pad. The final products are cut into lengths of 6 to 24 meters, bundled into 2.5 to 5 ton packages, labeled and prepared for shipping. The welding process using the BW32 wire butt welding equipment begins with the two rods being placed in clamps. The equipment automatically aligns the rods using precisely parallel guide bars. Once aligned, clamps hold the rods in place. The automatic welding cycle begins, and the rod ends are heated by resistance until they become malleable. The two rod ends are then pressed together, creating a strong and uniform weld. The entire operation is automatically controlled, ensuring consistent quality. After welding, the equipment retracts and the rod is removed. The process is repeated with the next rod. The BW32 ensures high welding accuracy, strong welds, and reliable performance throughout the process, thanks to its robust and easy-to-maintain design. Lucchini RS's casting process includes mold design and creation, using VOD steel refining technology, melting high-quality steel in a heat treatment furnace, cooling the castings with water and workers, machining the products using grinding and turning processes. Iron and steel production begins with coke making, where coal is baked in coke ovens at 1,100 degrees Celsius for 24 hours. Coke is then pushed out, releasing coke oven gas and dust, which are captured through water-sealed chamber lids and dust hoods. The gas is treated using lamella separators and bag filters. Iron ores, such as hematite, magnetite, limonite, siderite, and pyrite, are prepared in the sintering plant, where they are partially melted at 100 to 150 degrees Celsius to form sinter. This sinter, along with coke and fluxes, is charged into blast furnaces. At temperatures up to 2,300 degrees Celsius, indirect reduction occurs, producing molten pig iron. Four blast furnaces operate simultaneously, each with hoods to extract dust during coke charging and tapping. Exhaust systems and filters including electrostatic and fabric filters remove dust from the gas streams. The iron is then transported in ladles to the steel plant. In the steelworks, oxygen is blown into the molten iron to oxidize impurities in a process called decarburization. Primary dedusting captures emissions from the tandem furnace, while secondary dedusting systems extract fumes from the hall and ladle furnace areas. All extraction ducts and channels are enclosed to enhance dust control. Environmental technologies include 44,000 bag filters installed in 2011, ensuring efficient capture of particulate matter. The system uses covered slag channels and modern eco-filtration units to reduce emissions and meet environmental standards throughout the process. The forging process begins with the heating of the billets in a rotary furnace until they reach forging temperature. After heating, the billets are transferred by hand to a powerful hydraulic open-die forging press. The glowing billets are repeatedly forged under the press to form the basic shape of the part, while improving the internal structure and eliminating porosity. Next, the billets that need to be forged in more detail and shape are sent to another forging press for more detailed alignment and shaping of the ring. There, the shank is rotated and aligned several times so that the forging press can forge the desired ring shape. The ring blanks are then water-cooled to harden. Next, the forged parts undergo additional shaping using a hydraulic press or a manipulator, depending on the shape required. Some parts are forged into long shafts or step shapes using successive pressing and rotating operations. During the process, high-temperature heat treatment is performed using precision equipment, and forging steps are monitored in real time to ensure quality. The process of making seamless steel wheels begins with magnets moving solid steel billets into place. A carbide-tipped saw cuts the billets into smaller blocks. A hydraulic ram carries each block to a 2,300 degrees Fahrenheit furnace to soften the steel. After heating, the ends are descaled in a chamber with a chain beater. The steel is then pressed under an 1,100-ton press to further remove the scale. Next, a worker adds charcoal to the center, which burns to create a lubricating powder. A 2,800-ton punch then pierces the center, forming a donut. The donut is reheated before being rolled into a ring. A support shaft supports the wheel, while rollers and conical tools stretch and shape the wheel. After the ring is rolled, a serial number is stamped and the wheel is shipped to cool. Once cooled, the wheel is heat treated to relieve internal stresses. Finally, the wheel is placed on a turntable where surface machining tools are used to achieve a smooth surface. The finished seamless steel wheel is now very strong, stress-reduced, and ready for use in heavy machinery, generators, or as a train wheel. Steel screws for freight cars are forged at high temperatures, then precisely shaped and machined. The threads are cut with automated tools, then heat treated to increase strength. Each screw undergoes quality control before being packaged and shipped to customers in Switzerland and Germany. The process begins by heating a steel ingot in a furnace until it is red hot. The heated steel ingot is then fed into a press to form a thick steel donut-shaped billet. Next, A hole is punched through the center to form a donut-shaped belt. This belt is transferred to a belt rolling mill, where it is gradually expanded in diameter and reduced in wall thickness through hot rolling. Throughout the process, the belt is reheated as necessary to maintain its ductility. The final product is a large diameter steel belt with precise dimensions and improved mechanical properties. The first red-hot steel ingot is lifted by a manipulator and placed under a large forging press. The blacksmith clamps an iron ingot on top of the steel billet, so that after each blow, the press repeatedly strikes down to create a hole in the steel ingot into the desired shape. Another person scoops steel scraps into the hole created in the steel ingot, then continues the forging process. The forging press clamps the steel ingot and changes ends to continue the forging process. The copper production process begins with high-quality MOO and M1 copper, which is processed at the copper recycling plant with a monthly capacity of 800 tons. The copper is melted and cast into ingots, which are then hot-rolled into wire rods with diameters ranging from 8 to 25 millimeters. These rods are further processed through rolling and drawing operations to produce flat copper bus bars. Both soft and hard bus bars are produced, with widths up to 250 millimeters. After the production process is complete, the copper rods and bus bars are packaged and shipped to the warehouse for export. The aluminum billet casting process begins with the melting of aluminum in a gas furnace. Once melted, the aluminum is transferred to a degassing machine to remove hydrogen and impurities. The purified liquid aluminum then flows through a washer onto the casting table, where billets or bars are formed using the direct cold casting method. During the casting process, surface impurities are removed by skimming. After solidification, the billets are removed from the casting table and transferred to an automatic billet cutter. Here, the billets are cut to the required size using a saw. After cutting, the billets are transferred to a testing table for inspection. This step ensures dimensional accuracy and quality. The process can also include laser marking to track production data. The entire line from melting to cutting operates in a continuous and automated sequence, providing a turnkey solution for efficient billet and bar production. SANY's cutting-edge global lighthouse factories, highlighting advanced automation, intelligent systems, and high efficiency across various production lines. At the heavy truck factory, robotic arms assemble truck cabins with precision. The drilling rig factory integrates robotic welding and automatic transport systems. In the medium, small, and mini excavator factories, components are processed through fully automated machining centers, followed by smart assembly lines. The large excavator factory demonstrates synchronized robotic assembly for heavy components. The Huawei factory utilizes digital systems for real-time monitoring. The STE speed reducer and slewing bearing factories adopt CNC machines and AGV logistics for continuous flow production. The concrete machinery factory features automated frame welding and intelligent painting lines. At the secondary manufacturing factory, various attachments are fabricated with flexible robot-assisted cells. The petroleum equipment factory and special purpose vehicles factory integrate modular assembly techniques. The Zhongxing factory, especially the long cylinder production line, shows seamless robotic welding. The concrete batching plant factory highlights precision mixing equipment production. At the Huayuan Road Machinery Factory, paving and rolling equipment is built using smart stations. The large tonnage mobile crane factory and tower crane factory use smart handling and positioning systems, while the medium and small tonnage crawler crane factories rely on intelligent hoisting and assembly. Both small and large port machinery factories integrate AGVs and 3D inspection. The off-highway mining truck factory and hydraulic support factory emphasize structural strength through robotic welding. Finally, blade factories in Zhangjiakou and Shaoshan and the Beijing SANY Heavy Energy Lighthouse factory illustrates wind blade production with composite layup automation and real-time tracking systems. The servo press line at the Mercedes-Benz Bremen plant begins with fully automatic blank supply by AGVs and an automatic racking system. Schuller's servo direct press line, equipped with a blank loader, crossbar feeder, and end-of-line system, ensures high-speed, flexible operation. Tooling and die changes are fully automated and completed within 3 minutes. Each press gap uses only one tooling set, and slide movement is freely programmable. The ergonomic outfeed and user-friendly interface further enhance efficiency and part quality. The SA315S high-speed press operates in a fully automated process to manufacture rotor and stator stacks. First, coils are loaded onto the double decoiler. The strip is then automatically fed into the press. A non-contact strip thickness measuring device moves along the material to ensure precision. Once inside the die, the strip is punched to form electrical laminations. These laminations are stacked directly into rotor and stator packages under the control of the Schuler press packing system. After punching, finished rotor and stator stacks are automatically removed. All machine components, including automation and measuring devices, are fully integrated into the press control system. The press table is motorized and extendable to facilitate setup. The clamping plate is segmented for flexible tool use, and retractable tool change consoles ensure quick and efficient die changes. The SA315S enables high productivity, reduced tool wear, and high part quality, even for large format tools up to 4 meters. The process begins as an operator loads up to 10 PVC profile bars into the magazine. These bars, with a maximum width of 130 millimeters, are automatically transported to the saw unit. The saw is equipped with multiple blades capable of cutting at 45 degrees front, 90 degrees, and 45 degrees rear angles. The profiles are cut into precise lengths, typically between 500 millimeters and 4,000 millimeters, depending on the production requirements. The cut pieces are then transferred onto a buffer conveyor, which acts as an intermediate station to optimize workflow and prevent downtime between sawing and machining. Next, the profiles move into the machining center. Here, up to 30 routing and drilling tools are available for various operations, such as slotting, drilling screw holes, milling drainage channels, and cutting grooves. Each task is completed automatically based on the programmed job. Before drilling, if the profile includes a steel reinforcement, the system activates a pivotable screwing unit. This unit aligns and fastens the steel insert directly into the PVC profile. The patented rotating head allows the screwdriver to work at multiple angles without repositioning the profile, increasing both speed and accuracy. The screwing process is synchronized with the drilling to maintain a smooth workflow. The machine is programmed to handle left to right to left, U-shaped or Z-shaped profiles according to design specifications. Once the operations are finished in the first machining module, profiles can automatically continue through additional machining stations if the system has been expanded. Up to 3 SBZ 609 modules can be linked, each operating independently with its own control system but communicating interactively. Finally, the finished parts are unloaded. Depending on the setup, they can be sent to a transport table, a conveyor, or an automatic destacking unit that places them into profile trolleys. The entire process is highly automated, precise, and designed for maximum productivity in window and door manufacturing. The Fagor servo transfer press begins by automatically feeding blanks. An electronic transfer system moves parts precisely through multiple die stations. The servo press executes high-speed stamping with pendulum motion. Ribbon-Earth vision technology inspects each part for defects. Automatic die change and synchro software optimize the entire stamping process. The razor production process at Jiangsu Liu Razor begins with stainless steel strips that are inspected before entering a punching machine to form blade shapes. The blades then undergo a 4-step heat treatment: heating above 1000 degrees Celsius, cryogenic cooling, reheating to restore flexibility, and molecular restructuring for hardness. For double-edged blades, branding is printed onto the blade surface. Next, blades enter a grinding and polishing machine with 3 grinding stations: pre-grinding, fine grinding, and accurate grinding, producing 2 sharp edges. A polishing machine removes any remaining fragments. Then, a cut-off machine trims the strip into individual blade shapes. After inspection, the blades are washed and dried. In the third stage, the blade edge is coated with special materials, including Teflon and chromium, followed by heat treatment to enhance durability. Blue light inspection checks edge consistency, and laboratory tests confirm hardness and sharpness. Double-edged blades are then individually wrapped in wax and colored paper and boxed by automatic packaging machines. Plastic razor components are produced by 35 fully automatic injection molding machines. Mold development and maintenance are supported by in-house machining facilities. In the automated assembly workshop, razors are assembled at a rate of 180 heads per minute, including blade fitting, lubrication, protector, and handle connection. Finally, razors are packaged in high-frequency blister packaging lines at up to 120 sets per minute. Various types of packaging are completed in a dust-free workshop. All finished products undergo final quality inspection to ensure they meet customer specifications. Toshiba JSW Power Systems, a joint venture formed in 2008 between Toshiba and JSW Group, is Toshiba's only overseas thermal power equipment manufacturing facility located in Tamil Nadu, India. Operational since 2011, the company produces supercritical steam turbine generators ranging from 500 to 1,000 megawatts. It has become a market leader, supplying key projects across India, including Mundra, KGI, and Harduaganj. The facility houses the world's largest turbine balancing tunnel and has delivered Toshiba's first made-in-India 800 megawatts turbine. Committed to the Make in India initiative, Toshiba JSW supports India's rising energy demand with advanced, cleaner power solutions. The process of inserting folded filaments into the roller core begins with securing the roller on the rotating fixture of the machine. Folded synthetic filaments are automatically fed from the hopper and cut to the specified length of 200 millimeters. The machine's drilling and tufting head first drills holes into the roller core at pre-programmed positions. Immediately after drilling, the same head picks up a folded filament and inserts it into the hole using a clamping and pushing mechanism. The folded part of the filament is tightly forced into the hole, anchoring it securely. The roller then rotates incrementally to align the next hole position. This indexing process continues in a precise sequence, ensuring uniform spacing and density of the tufts across the roller surface. The speed of drilling and tufting is adjusted by an inverter to suit the material type and tufting density. The machine operates in either auto or step mode, and the process repeats until all tufts are in place. The large cone is positioned on the flanging machine. The rotating arm presses along the edge, gradually forming the flange. The operator adjusts pressure and speed to shape the cone uniformly. This process continues until the entire circumference is flanged according to the required diameter and thickness. The parts are first subjected to a 5-stage ferric phosphate pretreatment, followed by a deionized water bath and a sealing step. After pretreatment, the parts are dried and transferred to the paint booth, where the electrostatic powder is sprayed using both automatic and manual spray guns. After coating, the parts are transferred to a flash oven, where they are baked at a temperature appropriate to their size and shape, completing the powder coating process. Heavy fabrication at Newburgh HFD begins with plate cutting and edge preparation, followed by rolling and welding of shells. These shells are then assembled into large vessels and structures. Non-destructive testing, including radiography and ultrasonic testing, ensures weld quality. Post-weld heat treatment is performed for stress relief. Components undergo machining, sandblasting, and painting. Finally, the equipment is fitted with nozzles and internals, inspected, and prepared for dispatch. This streamlined process enables the production of pressure vessels, reactors, heat exchangers, and columns to global engineering standards. Metal parts are machined, welded, and assembled using advanced CNC machines and robotic systems. Components undergo quality control, heat treatment, and are tested under simulated operational conditions. Finished equipment is shipped via in-house stocks. Additive manufacturing and certified laboratories support continuous innovation. The MUL-to-USB 252 ARM-ROID begins by automatically loading the metal workpiece with its built-in robot. The main spindle grips the part while the B-axis milling head positions precisely. The machining starts with internal boring, followed by external turning to form the general cup shape. Next, the contouring of the outer surface is done using synchronized B-axis movement and C-axis rotation. The milling spindle machines the handle connection points using CAPTOC6 tooling. The process continues with internal threading and fine finishing of the inner surface. Finally, ARMROID unloads the completed metal coffee cup, completing the fully automated, high-precision multitasking cycle. The machining process begins with B-axis face turning using a VCMT insert on C45 material. The B-axis swivels from 95 degrees to -10 degrees, cutting at a depth of 0.5 millimeters, a feed rate of 0.25 millimeters/rev, and a cutting speed of 300 meters per minute. Next is ID skiving roughing on a gear with module 2 and 32 teeth. The tooth height is 2.2 millimeters, with 4 cuts ranging from 0.3 to 0.8 millimeters in depth. Feed rate is 0.26 millimeters/rev. M spindle speed is 3,696 minutes, and main spindle speed is 1,271 minutes. The process continues with OD skiving roughing on a module 4 gear with 19 teeth and 9 millimeters tooth height. 8 cuts are made, with depths from 0.44 to 1.76 millimeters, a feed rate of 0.3 to 0.6 millimeters/rev, and both spindles at 1,381 minutes. The camshaft production process on the Felsomat FTC 180 begins with the automatic feeding of the raw lobe components. Each workpiece is picked up by a gantry loader equipped with robot grippers and precisely placed into the machining zone. The FTC 180 uses pendulum machining with 2 spindles, allowing one part to be machined while the other is loaded or unloaded, minimizing idle time to under 1 second. The machining starts with green turning, a high-performance dry process that shapes the soft lobe using direct drive spindles and CAPTOC5 tooling. The monoblock machine base ensures maximum stability and micron-level precision during contour cutting. The process includes external turning of the lobe's profile and internal boring for the joining bore. The turret quickly switches tools via a hearth coupling system, ensuring continuous accuracy. Following the initial turning, the lobes are inspected and then transferred to laser structuring. A laser modifies the inner diameter surface to create microtextures for stronger form-fit bonding in the upcoming joining stage. The lobes are then assembled onto a tube using an internal high-pressure hydraulic forming process. The steel tube is plastically deformed under up to 2,500 bars, while lobes are only elastically deformed, creating a tight, secure fit. A post-process gauge checks the bore's roundness and diameter to ensure tight tolerances are met, compensating for tool wear. The lobes are then stacked, using a dedicated handling system to avoid damage. Each lobe is marked with a DMC code for traceability due to the high part variety. With a machining time under 5 seconds per lobe, the FTC 180 delivers unmatched efficiency in camshaft production. At Brück GmbH, we offer complete in-house machining of large complex components, including turning, drilling, milling, and gear cutting. We handle diameters up to 6,500 millimeters and work with steel, copper, and aluminum. Our advanced machines perform high-precision operations, including 5-axis simultaneous machining and combined turning milling in one setup. We ensure tolerances within hundredths of a millimeter and verify them with 3D coordinate measuring under climate-controlled conditions. Gear cutting is also available for parts up to 7 meters in diameter. The crash test was performed on a Hardinge AHC automatic lathe, not CNC, using Cobra Ludlow Steel HSS tool bits. The lathe operated at 3,000 RPM with a 0.150-inch depth of cut and a 0.750-inch length of cut on 416 stainless steel. The feed rate was approximately 3 to 4 inches per minute. Each tool was tested to destruction. Only 2 out of 12 tool bits completed cuts on more than 10 parts, showing minimal wear and the potential to continue. The next best tool failed on the 4th part. Tool performance varied significantly under identical conditions. The cutting process begins with the configuration of the mobile ABR-AJET 700 system developed by Waterjet AS. The system generates a high-pressure water stream at 700 bars, combined with a controlled stream of abrasive particles, usually garnet. This abrasive water mixture is directed through a precisely focused nozzle with a small orifice, creating a high-speed water jet capable of cutting materials up to 150 millimeters thick. The nozzle is mounted on a CNC-controlled multi-axis arm, allowing for precise 2D and 3D shaping. Offline programming is used to define the cutting path, ensuring the precise execution of complex geometries. During operation, the cutting head follows the programmed contours to perform straight cuts, internal and external cuts, bevel cuts, and even pipe cutting. The process is completely cold, avoiding thermal deformation or structural changes in the material. In the video, both flat sheet metal and curved surfaces are cut cleanly, with excellent edge quality and minimal kerf width, demonstrating the technical efficiency of the Aggregate Waterjet cutting system. First, the yacht is loaded onto a multi-axle, self-propelled modular transporter that uses beams and brackets to stabilize the hull. Once stabilized, the convoy carefully navigates narrow roads and around tight corners, with escort vehicles ensuring safety and clearance. The transporter moves slowly to maintain balance and avoid obstacles. Once at the launch site, a final alignment is performed. The yacht is then transferred to a floating platform for launching. Throughout the journey, specialized equipment and expert coordination ensure the structural integrity of the yacht and its precise arrival at the launch point on the water. The mobile pump VENERONIETR 55ths is transported to the site and positioned near the water source. Flexible suction and discharge hoses are connected. The pump is started, and its powerful propeller system begins drawing water at a high flow rate. The hydraulic mechanism efficiently lifts and transfers water through the discharge hose. The water is then redirected to a designated area for flood control. Throughout the process, the pump operates steadily, maintaining a high output of up to 1,000 liters per second, ensuring rapid water removal from the flooded zone. The technician begins by positioning the new super single tire in front of the hub. He carefully pushes the heavy wheel toward the hub, aligning the bolt holes with the studs. Using both hands and body weight, he rolls and shifts the tire until it partially fits onto the hub. To ensure the wheel seats properly, he uses a long tire iron to make fine adjustments. He inserts the tool between the rim and hub flange, prying and nudging the wheel gently to center it. The tire iron is used repeatedly on opposite sides to evenly adjust the fit. As the wheel gets closer to its final position, the technician checks the alignment of the bolt holes and ensures the tire sits flush against the hub face. Once aligned, he gives the wheel a firm push, allowing the studs to protrude through the holes completely. The tire is now ready for lug nut installation. The demolition of the Lagotera Dam on the Bernesga River began with the construction of a ramp using sediment from an old river basin and concrete debris to provide access for machinery, respecting the riparian vegetation to stabilize the material. Dismantling began at the dam gate area, removing mechanical components and renovating the gate mechanisms. The Castilla and Leon Fisheries Department used electrofishing to save aquatic life, which required repeated sweeps due to the high fish content. An opening in the back of the ring channel allowed for a controlled reduction in water levels. The opening of the gates lowered the water level to less than a meter, initiating the process of mobilizing sediment, mainly gravel and decimeter-sized blocks with some sand areas. This minimized downstream impacts and maintained water quality for aquatic life. The channel area was reinforced with concrete blocks to allow machinery access to the wall. The reinforced gates were gradually dismantled, separating the metal from the concrete to selectively remove debris. A 1-meter deep central opening in the dam lowered the water level further, exposing sediments that had accumulated over 90 years and formed the original rapids. The demolition process was accelerated when the wall, made of unreinforced stone and concrete blocks, was carefully removed and placed at the top of the dam to minimize debris in the lake. The lowered water level increased the river's flow, mobilizing sediment to fill the deeper areas of the lake. Fish migrated upstream due to the faster flow. After the concrete structure and foundation were removed, all debris, including angular blocks and scrap metal, was cleared from the river. The materials were placed close to the channel for minimal restoration until the river's peak flow completed the natural recovery process. Within 2 days, the reservoir was drained and the river began to reshape its course, transporting large amounts of sediment downstream within 12 hours, addressing the sediment deficit in lower reaches. The construction process begins with the creation of a solid concrete foundation and drilling precise anchor holes into the rock according to geotechnical surveys. Next, high-strength steel anchors are inserted and grouted to form a stable connection to the rock. A reinforcing cage is assembled, followed by the establishment of formwork for the concrete foundation. The concrete is then poured, anchor heads and reinforcing steel embedded. After curing, anchors are tensioned to secure the structure. Finally, the foundation is leveled and prepared for the installation of the wind turbine tower. Throughout the process, analytical calculations and 3D simulations are used to ensure the stability of the structure and optimize the design based on the initial ground conditions. To rehabilitate the damaged B70 road near the Sven-Heufelder Moor, a highly efficient and durable method was chosen, the inline pave technique combined with asphalt reinforcement grid installation. This process was executed by GS GmbH and Gerhard Herbers GmbH and completed within just 3 days. First, the old asphalt surface was milled to prepare the base. Following this, a geogrid type HTELITC40 was directly applied onto the milled surface. This reinforcement mesh helps prevent the formation of fatigue and reflective cracks, thereby extending the service life of the road. Next, the inline pave train began its operation. It consisted of 3 main machines working consecutively: the Vogele Montana 3000, offset power feeder, the Super 2100 paver for the binder course, and the Super 1802 for the surface layer. Importantly, the process follows the hot-on-hot method, where the binder and surface layers are laid in a single pass while still hot, ensuring excellent bonding. The MT3000 offset power feeder is responsible for material delivery. Using a heated, swiveling conveyor belt, it supplies hot mix alternately to both pavers. The operator controls the material flow with a joystick and a traffic light system that signals which type of mix binder or surface is needed. With a delivery capacity of up to 1,200 tons per hour, trucks can unload 25 tons of asphalt in just 60 seconds. Following this, the Super 2100 paver installs the 10 cm binder layer using high compaction technology. Despite the compaction, the reinforcement grid remains stable and unaffected. Immediately afterwards, the Super 1800 applies the 2 cm surface layer directly onto the hot binder layer. Its insulated 25-ton hopper and integrated transfer module ensure a continuous supply of hot mix. Additionally, automatic spacing controls and safety bumpers maintain safe distances between machines. Finally, HAM DV90 tandem rollers with oscillation compact the layers without displacing material ideal for the thin surface course. In conclusion, this innovative inline pave method with integrated reinforcement results in a long-lasting, crack-resistant pavement while significantly reducing construction time. The concrete slab cutting process begins with the slab being strapped down and lifted. The worker uses a wire saw blade to cut through the slab smoothly without vibration or damage. The diamond wire moves continuously, cutting through both the concrete and the steel without disturbing the steel. The installation of the light steel frame floor system begins with drilling and positioning the vertical and horizontal steel beams to form the supporting structure. OSB3 panels are then placed on top of the structure, followed by the installation of galvanized steel panels to form the lightweight floor base. EPDM acoustic strips are placed along the steel frame to reduce sound transmission. Workers secure the panels with screws to ensure stability. Once the steel panels are installed, workers use floor nailers to secure each layer of wood to complete the floor. This system allows for a lightweight yet sturdy floor, allowing for flexibility in the final surface material and eliminating the need for traditional concrete panels. The branches and rotten wood are fed into the head of the pellet machine PM11, where they are first separated and crushed into smaller particles. These particles then move into the pressing section, where the material is compressed through a die to form uniform wood pellets. The machine has a dosing silo that ensures a precise amount of raw material is fed into the press, preventing clogging and ensuring continuous operation. The pellet length and final sieve size are adjustable. The finished pellets fall out from the bottom, completing the process efficiently in a compact 3-in-1 unit.